Hello, thank you for being here. My name is Minsun Jeon from Jeon University. Today I'll be presenting Seeing Through the Blur, Unlocking Defocus Maps for Deepfake Detection. My research addressed the critical challenge of deepfake detection. The technical difficulty lies in the rapid advance of generative AI models. It has become increasingly easy to create fake images that look realistic, sometimes even more perfect than real ones. For instance, this slide shows a real photo on the right and the AI-generated portrait on the left. Both appear visually convincing. This raises a fundamental question. When everything looks real, what truly defines the real images? The key distinction lies in the creation process. Real images are the original capture from a camera that operate according to the laws of optics. We define deepfakes as an image produced by AI generative model. While they may appear blurry reason, the blur is often artificially added for aesthetic and lack physical accuracy. So to detect what's real, we turn to something that only real cameras can produce, defocus blur. So what exactly is defocus blur? It happens when a camera cannot focus on everything at once, so objects further from the focus point look blurry. As you can see in this very strong example, this is an out of focus image. But the key point is this: defocus blur is not just found in these extreme cases. In fact, due to the optical limits of lens, every single real photo inevitably contains some defocus blur. This phenomenon is governed by a principle called depth of field, or DOF, which is determined by the camera's aperture setting and scene geometry. And this is the gap. While AI excels at creating visual plausible 2D images, it struggles to perfectly simulate the complex physics of 3D depth, or lens optics. As a result, AI-generated blur can often appear unnatural, ignore depth cues, or be physically inconsistent. Therefore, our core idea is to analyze these physical fingerprints of authentic blur to distinguish it from the artificial blur found in deepfakes. Existing detection methods which learn fake artifacts or content-dependent signals have limitations. As AI models advance, artificial becomes less obvious and models overfit to spurious correlations. Our approach is different. We focus on real images using a key physical signal defocus blur, which is universal and hard to mimic. This method allows us to visualize the defocus map and see precisely why the model makes a decision. To validate these insights, we formulate three key research questions to guide our study. First, do defocus blur patterns differ between real and fake images? Second, can this pattern improve detection performance? Third, does the model actively use defocus pattern in its predictions? This is overview of a methodology. We design our experiment to answer these questions. First, to answer RQ1, we conduct a feature-level analysis. The goal is to verify if the defocus blur map itself contains the discriminative information to separate real from fake. Then for RQ2, we ask, so how much better is the detection performance? We just compare the results when using the RGB input versus using our defocus input. Finally, for RQ3, we use sharp values to visualize and mathematically verify that our model is actually leveraging the defocus blur to make its decisions. Here is our experiment setting. Before diving to the result, let me briefly explain how we generate the Defocus Blur Map. As we can see in this example, we define the Defocus Blur Map as a pixel-wise representation of blurriness, with values from 0 to 1. Black represent a sharp region, white represent a blurry region. To generate these maps, we adopted a well-established edge-based algorithm proposed by Jeon and Jeon. Our pipeline is shown below. We take an image, generate defocus blur maps, feed them into a backbone, and classify it as a real or fake. This is the deepfake detection performance on FF++ dataset. Our defocus-only model achieved an AUC of 0.99, outperforming the original RGB exception net at 0.96. The key takeaway is that we use the same exception backbone. We simply changed the 3-channel RGB with our 1-channel defocus map. Achieving higher performance with less information proves that the defocus map is a more powerful and compressed signal than RGB. Next, I will present our feature level analysis result. This addresses our first research question. Can the defocus map itself tell real from fake? The answer is yes. And we show this in 2 ways. First, the TSNE plot on the right. We show the clearly separable groups in the plot. Second, on the left, the binary mask. The binary mask shows us difference. It highlights in white where the pixel difference between the fake and real map is greater than 0.1. We ran this test on 6,400 pairs and found a consistent 5 to 9% mismatch according to the fake types. This confirms that the AI generation measurably changed the defocus blur patterns. Now we move to our final and most critical question. Does our model actually use the defocus blur? To answer this, we conducted a model level analysis. First, we used the XAI tool SHAP to visualize where the model is looking to make its decisions. In the map shown on the right, the area with red dots are the pixels that most strongly influence the model's prediction. Second, we use our binary mask shown on the left as the ground truth. The core question is, do these 2 maps align? The image you see here can be represented by the following graphs. As you can see, the x-axis is a defocus value grouped into bins of 0.1. The y-axis is a pixel count shown as a normalized weight. We use this because the SHAP map and the binary mask have different total pixel counts, and this is essential for a fair comparison. In this chart, the purple bar represents the ground truth defocus difference, and the yellow bar represents the SHAP value. The final alignment score is the histogram intersection. We just simply take the minimum value of the 2 distribution at each bin and then sum them all up. A higher score means the model is looking at the right place. Quantitatively, we computed the average alignment score over 1,000 fake images for each fake types. And the defocus model shows consistently higher alignment score across all samples. To conclude, I'd like to summarize the main contribution of our study. First, we propose a novel approach. To our knowledge, this is the first study to use defocus blur as the main signal for deepfake detection. Second, we showed It has strong performance, achieving 0.99 AUC on FF++. Finally, through a series of experiments at both the feature level and modal level, we have comprehensively validated that defocus have indeed an effective and interpretable signal for deepfake detection. We hope this work contributes to building more trustworthy media forensic systems. I will conclude my presentation. Thank you for listening.